Hey guys, Mr. Martin with the video over power series. First thing is grab a separate sheet of paper. We're only doing 3 examples, but each of these examples requires half a sheet to a full sheet of paper. All right, so let's talk about a power series. All right, we've discussed infinite series. An infinite series is basically a series of numbers that we add out to infinity. Sometimes they converge, sometimes they diverge. We're basically interested in where the series converge, meaning they have a sum. If we take this series of constants, we have 5 to the n divided by n factorial. So we'll get like 5, 25 over 2, 125 over 6, 625 divided by 24, and so forth. And we end up with 5 to the n over n factorial. This is what we call a series of constants because each one of these terms is a constant. And also each one is a power of 5 multiplied by some other number. If we take this concept and extend it out to a function like x minus 5 to the n over n factorial, we end up with what we call a power series because every term of the series is x minus 5 to some exponent. Generally speaking, we can extend an infinite series to be written as an times x minus c to the n power. Small thing is, this looks a lot like a geometric series because a geometric series is formed by multiplying by the same thing to get to the next term. So if we notice this an times x minus c to the n power, to get to the next term, we basically just multiply by x minus c. Then if we have this centered at x equals c, is basically this. Now, well, all of these a1s are really just an times all of these terms. We could, in this example, we could say a subscript I just equals an. It's just written in this form so that every term has a coefficient. So the domain of a power series is the series of values for which the series converges, which means that the series has a sum. What we're going to be doing in these examples is finding the domain of these power series. For a power series centered at x equals c, one of 3 things could happen. The series only converges exactly when x is that value, or there's some value r where our series converges between like 2 numbers. It means something like if we had x minus 3 is less than 4. That means that between -4 and +4, x minus 3 converges. And it converges outside of that, or the series is convergent for every possible value of x we could think of. This value r is called the radius of convergence. If the series only converges at x equals c, we're going to find out that r equals 0. If the series converges for all values, we're going to get that r is infinity. The restriction that we get for our convergence is called the interval of convergence. When we're determining our interval of convergence, we also need to check the endpoints. That's going to mean that sometimes if we have this inequality, we're going to include an equal bar maybe. I think one of the tests that we haven't discussed is the ratio test. The ratio test is going to give us our radius of convergence, and that's going to help us find our interval of convergence. So the ratio test is if the limit as n approaches infinity of the n plus first term over the nth term is less than 1, the series is going to converge. This is a very easy limit to find, and it involves canceling most of the terms of our series. So in our notes, we're going to start with this first example, if I can find it here. We're going to find the interval and radius of convergence for this infinite series, this power series. So again, this is not nearly enough room to work this, so we're going to copy this down and work it on a separate sheet of paper. So we have the sum from n equals 0 to infinity of -1 to the n plus 1 power times x minus 5 to the nth power over n times 2 to the nth power. So what we want to do is find the radius of convergence and the interval of convergence. And to do so, we're going to use the ratio test. So to set up the ratio test, first we have to have absolute value, which means that we just don't need to include the -1 in our limit. So I wrote that too big. We're gonna have the limit as n approaches infinity of, so our n plus first term, all right, so first let's set this up. We're gonna have a to the n plus 1, or a subscript n plus 1 over a n. That is going to equal the limit as n approaches infinity. If we have a n plus 1, it just means substitute n plus 1 into this sequence to find the next term. That's going to be x minus 5 to the n plus 1 power over n plus 1 times 2 to the n plus 1. And that is going to be divided by an. And an, again, is this sequence without the -1. So it's going to be divided by x minus 5 to the n power, which is then divided by n times 2 to the n. One of the things that we're going to do immediately most of the time is never do this division and instead multiply by the reciprocal of our sequence. This is going to equal the limit as n approaches infinity of x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1 times, now again, we're multiplying by the reciprocal of this, so it's going to be times n times 2 to the n divided by x minus 5 to the nth power. And we know that doing the ratio test that this entire limit should always be less than 1 in absolute value. So this is less than 1. Now, if we take some steps to, I'm sorry, you can't see the less than 1. So if we take some steps to rewrite this, zoom out just a bit, we're going to continue over here. So if we're looking at this, x minus 5 to the n plus 1 divided by x minus 5 to the n, we subtract the exponents. So n plus 1 minus n is going to leave us with 1x minus 5. So we're going to have the limit as n approaches infinity. So far, we just have an x minus 5 left over, still an absolute value. And then we have 2 to the n plus 1 over 2 to the n. Same thing, we subtract the exponents. N minus n plus 1 is going to be -1, which means the 2 ends up on the bottom. So we have x minus 5 over 2 times, now we just have to worry about the n and the n plus 1. So we've handled this, we've handled this, we've handled this, and we've handled this. We need to worry about the n over n plus 1. Notice that we split this to be n over n plus 1. So in this limit, again, this is still less than 1. In this limit, we're going to end up with, this limit is for as n approaches infinity. So our x minus 5 over 2 is irrelevant when n goes out to infinity. So we're going to switch this to the outside. So we have x minus 5 over 2 times the limit as n approaches infinity of just the absolute value of n over n plus 1. And we're going to keep writing this limit, remembering that this should be less than 1. So, also we want the absolute value here. So, as n approaches infinity, this is the case where we have the degree of the numerator equals the degree of the denominator. So, this limit is 1 times x minus 5 over 2. So, this x minus 5 over 2 in absolute value is less than 1. Now, again, that's because we'll just do some side work. The limit as n approaches infinity, we don't even need the absolute value for this because n is positive. So n over n plus 1, this goes to, converges to 1. So we end up with x minus 5 over 2 is less than 1. So we end up with the absolute value of x minus 5 is less than 2. This 2 is our R value, our radius of convergence. So if we go back to Algebra 1 and even A2 trig, we're going to know that for an absolute value inequality, we're going to have -2 is less than x minus 5, which is less than 2. That's what it means for x minus 5 and absolute value to be less than 2. X minus 5 needs to be between -2 and +2. So to solve this inequality, we end up with, if we add 5, we're going to have 3 is less than x is less than 7. So our radius of convergence is the interval, our radius of convergence is 2, and our interval of convergence is 3 to 7. So this is our interval of convergence. So in the notes, we say that you should check the endpoints. So we're going to rewrite our sum down here. We have the sum from n equals 0 to infinity of -1 to the n plus 1 times x minus 5 to the n power over n times 2 to the n power. So we know for every value strictly between 3 and 7, this sum will converge. What we do need to check is the endpoints. So we're going to have two different cases. If x equals 3, we're going to get this sum. We're going to have the sum from n equals 0 to infinity. And if x is 3, 3 minus 5 is -2. So we're going to have -2 to the n power. So we're going to have -1 to the n plus 1 times -2 to the n power over n times 2 to the n. Let's do some side work. -2 to the n equals -1 times 2 both to the n power. So we're going to have -1. So this is going to be -1 to the n times 2 to the n. Now, we already have a -1 here. So if we have -1 to the n added to this is going to be the same as having the sum from n equals 0 to infinity. So -1 is, we're going to have -1 to the, we add the exponents. N plus 1 is 2n plus 1, which is always an odd number, times 2 to the n over n times 2 to the n. This is the equivalent of having the sum from n equals 0 to infinity. The 2 to the n's cancel so that we have -1 to the 2n plus 1 over n. So we don't need, so since n is always, since all of our terms are going to be negative, we don't even need the 2n plus 1, really. We can not consider it. But does this series converge or diverge? If it converges, we include 3 as part of the answer. If it diverges, we do not. So just based on the p series, we have, this is equivalent to just 1 over n, which we know diverges because p equals 1. So we're going to put divergent because p equals 1. So we don't include the 3. The second case is if x equals 7. If x equals 7, this is going to be 7 minus 5, which is 2. So we're going to have 2 to the n over 2 to the n. So we're going to have, to save some steps, we're going to have the sum from n equals 0 to infinity of just -1 to the n plus 1 over, again, if this is 2 to the n, on the bottom, the 2 to the n also cancels. So we have -1 to the n plus 1 over n. So this is an alternating series. Depending upon the term we're at, we're going to have a negative or a positive answer. Remember, for an alternating series, to check if it's convergent, we have to check if the terms alternate in sign. So one, they do alternate in sign, check. The second thing is, do they decrease in magnitude? The answer is yes. So decrease in magnitude. The answer is also yes. And then the third thing is the limit as n approaches infinity of 1 over n equal to 0? And the answer is yes. So this series does converge, and so we're going to add that in. Now, we should note that this is not absolutely convergent, because if it's absolutely convergent, we're just going to have the sum from n equals 0 to infinity of 1 over n. And remember, the harmonic series does not converge because p equals 1. So this is conditionally convergent, but it does converge. So we do include 7 as in our answer. So the answer to this is our radius of convergence is equal to 2, and the interval of convergence is from 3 to 7. 7 is inclusive. So I'm going to split this into a second video because this example is long and the next two examples are equally lengthy. So I'll see you in part 2 of Power Series.